Welcome back to ECE 320A. Homework number 1 is due today. Hopefully that does not come as too big of a surprise. If it does, you have a few hours to submit it. It's due at 11:59. Homework number 2 is due in a couple of weeks or whenever the 12th of February ends up being. That's probably on a Tuesday. Exam number 1 material should be on the website in its own little module for exam number 1. And do you want an exam number 1 review session? We could maybe have that after class on the 12th. That's what we will plan on then. Is I don't think this room is being occupied after we finish, so I'll see if I can verify that or gain access to this room, and if I don't, then we'll figure out where we can hold that review session. But that will be prior to, and I need to, if I haven't already, there should be a quiz on D2L. It's not a quiz per se, but it's a location for you to submit a question or a topic that you would like covered in the review session, or you can recommend or suggest. So in the quiz for exam number 1, you can go in and you can say, I would like you to explain a little bit more effectively some topic, or you might say, I'm having trouble understanding this example. That might be what you could submit in the quiz section of D2L for exam number 1. Today what we want to do is continue with three-phase circuits or three-phase material. That's chapter 11, and actually that will be all on exam number 1. I was asleep at the wheel when you asked that question before, but all of three-phase will be on exam number 1. It won't be split between exam 1 and exam 2. Single phase and three-phase power will be exam number 1. We'll talk about the different, interconnection restrictions. Basically, I'll just tell you, you can't interconnect a positive phase sequence with a negative phase sequence unless you want fireworks or danger or disaster. You keep positive phase with positive phase, negative phase with negative phase. Then we'll have a quiz concerning three-phase circuits, and that will hopefully then lead us into the different kinds of connections we can have with our sources and our loads. Each of those can be configured either in a Y configuration or a delta configuration, and then we can have the 4 different combinations of sources and loads, where typically the convention is the first symbol in that pair of symbols is the source, the second one is the load. If we now say we have a Y-Y interconnection, that says that your sources are connected in a Y configuration and your load is a Y configuration. If you had a Y delta, your source is a Y and your load is a delta configuration. That's allowed. That can happen. And we'll look at those. Then we will look at how to compute per phase power. Now we have 3 phases. So we could look at the power in phase A, in phase B, and phase C at the source, in the transmission lines, at the load. All sorts of different ways to ask you questions about power. And complex power, we now have to figure out what is actually the phase voltage and what is the phase current. We then do the VI star for that phase voltage and phase current to compute the complex power of a particular piece or phase in our system. Then if our system is balanced, that means all 3 phases look the same in terms of complex power, and we can simply multiply that per phase power by 3. And that gives us our total complex power of that, let's say, interconnected load, interconnected source, depends on what we're interested in. Where you get confused is keeping track of maybe you won't, but generally it's more challenging to keep track of what do you mean a phase voltage and what do you mean a phase current. What those represent depend on how the source or the load is interconnected. So in a Y configure, well, we'll get to that, but sometimes the phase current is the same as the line current. Sometimes it is not. It depends on how your systems are, or subsystems are interconnected. Yes? So all of these, the question was those are RMS voltages and currents, unless I claim otherwise, you can probably assume that it's RMS. But if it's not clear on the exam, you write down what you're assuming. You can say, I'm assuming RMS. But if I give you a time domain waveform in an equation, typically that will be a maximum value for the amplitude, and you'll have to convert that to an RMS value if you're going to use VI star. If you're using maximum values, then you have to put that 1/2 factor in, and why worry about keeping track of a 1/2 factor when if we just convert everything to RMS, we can just remember VI star. And then we'll try to illustrate or justify how we can take a three-phase interconnected system and actually extract from that a single-phase equivalent, which really means we can go from a Chapter 11 problem back to a Chapter 10 problem and analyze a single-phase system. And if everything's balanced, no matter what you determine with, let's say, an A phase, you can determine or state what's happening in the B phase and the C phase. That's where we're headed. Here are the fireworks that I mentioned earlier, the interconnection restrictions. This means don't do it, that big X. Don't try to interconnect a positive phase sequence with a negative phase sequence. That can't happen. If your system is a positive phase sequence, then everything in it needs to be interconnected in a positive phase sequence. Similarly for a negative phase sequence. And now you know how these spin, right? They hit you if you're standing still. If it's a positive phase sequence, what hits you first? A. Then what? B. C. So you just have to remember your ABCs even though you're getting hit, right? That's the positive phase sequence. Negative is ACB. But that's what I'm meaning by this phasor, and a lot of times this rotation of those phasors is not even acknowledged or written down, but it's there and it's doing it at a frequency omega, which for power problems in the United States is usually close to 377. 2 pi times 60. If that's the case, then if we use our A phase voltage as the reference, then we simply change the B phase and C phase by the appropriate phase shift of 120 degrees relative to ABC in this positive phase sequence discussion. If that's the case, then here's your quiz. What is the sum of these three phasors? No one heard that, did they? It was too quiet there. Heard what? So, what is the answer? What is the sum? And this is now a phasor sum or a vector sum. And why did somebody say 0, which is the correct answer? Well, if you now simply connect these phasors, A phase, B phase, and C phase, together, head to tail, you can hopefully see that if I now start here, well, I don't want red. Everybody gets nervous when red starts appearing. There's V sub AN as a phasor. Now you add to that V sub BN as a phasor, and I'm not going to probably be able to draw this, but didn't B go down at an angle of minus 120? So here is now V sub BN as a phasor, and you add to that V sub CN, which was going up at 120 degrees with the same length, and you get back exactly where you started. That's sort of the justification of why, if you have a balanced set of three-phase voltages or currents, their sum, their vector sum, their phasor sum is 0. And that's important, and we'll be using that a lot today. Questions on that? That was an easy quiz, apparently, but you won't be able to share your answers on the exam like that. 57! Oh, yes?
Can we measure like the phase of our voltage like from our outlets if we want it?
So now the question was, can we measure the phase coming out of the wall outlet?
I feel like it's going too fast.
I can't see. I feel like I'm being interrogated with these lights anyway from the projector. But can we, basically the phase depends on where you draw the line in the sand or on the tape or on the floor to define t equals 0. So if it's just plugged into the wall and you see this on the oscilloscope, you're going, okay, where do I define t equals 0? You could then say, oh, I'm going to peg it right here, and that could be right where it's peaking, for example, and now everything is relative to that. So in that sense, that's kind of like saying, I'm going to pick this as my reference phasor, and you just assign that phasor 0 degrees. Then everything is relative to that determination of where you said, oh, here's t equals 0. Here's my 0 degrees phase. So no, plugging something into the wall, you're just going to see an oscillating waveform. And you would have to then say, okay, where do I want to define 0? But plugging it in, you should be able to see 60 hertz, right? If you're in the United States. You'll see how quickly it goes. And what's the magnitude coming out of here? Okay. 110, 120. That's what you see labeled, but what is that actually? That's RMS, isn't it? So the peak is actually 120 on average times the square root of 2. Anybody have a calculator? That's up to about 170. Peak. 169.7. Okay, 170 if you round. So we have 170 degrees from 0 to peak. I just pulled something. Any other questions? No? People listening to this, they're going to go, what did he just pull? I don't understand. But sometime in the future, you can go back and replay this and go, yeah, there was something funny, well, you found it funny. No one else would. But where were we? Plugging something into the wall. It now is 0 to 170, minus 170. And then it does that 60 times a second. But you now know how to compute the RMS of that. You now divide that maximum by the square root of 2. Oh, this now, if you put it across a resistor, would look like 120 volt DC is the power that that resistor would sort of feel. It would get hot at the same rate or in the same way that somebody giving a sinusoid of 170 0 to max does in a sinusoid. That's what the RMS is telling us, that on average this looks like 120. All right. I'm just trying to loosen up a little. What do we have? We have a balanced three-phase set of voltages. And if we said we had the A phase, the B phase, and the C phase, they equal 0. And again, we're doing that with the phasors or the vectors. If their phasors add up to 0, what can we say then about if we actually added up the instantaneous waveforms? That's what I'm meaning now by these time domain. The capital with the bar are the phasors. This is now the instantaneous version of the A phase. That's this thing going up and down 60 times a second from 0 to 170 if it's at our particular apartment or house or in this building. What's that sum to? So now if you go back and look at all the, you would now have a sinusoidal expression. This one would, let's say the A phase is 0. The B phase has a phase of minus 120. So we're suppressing a lot of times in that phasor the omega t. But the argument on V sub A of t is omega t plus 0. This B is omega t minus 120. This V sub C is omega t plus 120. You do the trig, and it will also be 0. Instantaneous for all time. So if you added up those three instantaneous waveforms, you now have 0. So keep that in mind if we need it later. But we have two different ways that we interconnect or wire these three-phase voltage sources that we will play with or use in this course. We have a Y configuration where all of the negative terminals are connected, and we may go in and actually in the Y we may identify that as the neutral conductor. This is, let's say, V sub A. Let's say this is V sub B, and this is now V sub C. We can put an impedance in here. Let's say Z sub GA. Maybe here we have Z sub B with a G. That's our generator impedance in the B phase, and here we have Z sub GC. This point, if we need to identify it, might be A prime that separates the, but we won't be able to go in and access that impedance of our generator, but it's inside the terminals. Now if you have this three-phase generator, you can access A, B, and C. Those are the generator terminals at the source. And this is the Y configuration. That's one of the two possibilities. The other is the delta, which looks a little different, obviously. Now we have V sub A, but here is, let's say, Z sub GA. I shouldn't make these so close. Here is now the C phase and here is the B phase. And these are lowercase just to be with our convention. These are the lowercase letters that we're using when we're close to or at, whoa. I was trying to interconnect the, no, you can interconnect deltas and y's. It's just the phase sequences you can't interconnect. And it may be that it's easier to sort of pull those out a little bit and say, oh, here's my A, here's my B, and here's my C. And now if all of this was buried inside, now you just have the three terminals, A, B, and C, and this one internally is interconnected as a delta. The previous one, you could just have its terminals visible and it would be in a Y. What I haven't necessarily done in those sketches is actually to illustrate or parameterize what these Z sub G's look like. But if we did, we might say that we have some impedance and some reactance. So here is now, some resistance. Let's say that's R sub W. That's our winding resistance. And we have all of these coils that are wrapped around, look like an inductor, and so you have some reactance. Here's our winding reactance. Such that Z sub G, whatever phase, that's what the blank is for, Z sub G, A, B, or C, that's now going to be RW plus J XW. And sometimes we will neglect the generator impedance, and sometimes you'll have to incorporate it or deal with it or take it into account. But in these boxes that I've now labeled Z sub G something, you could actually fill them in with a little bit more detail, and they would have this winding resistance and winding reactance. That's what the sources look like that we will be using. The loads are similarly connected. So the loads can be Y or delta connected. There's, let's say, the A phase impedance of the load. This is now a Y connected load. Here's the B phase, and here's the C phase, and these are supposed to be capitalized so that this terminal now is the B, the A, and the C. That's the Y connected load impedance. And Z sub A, if they're balanced, Z sub A looks the same as Z sub B, looks the same as Z sub C. If it's unbalanced, they may look completely different. The delta is similar, and this Z sub A is not the same as the other Z sub A, so maybe I'll put a party hat on it. But here is now Z sub A. Here is Z sub C. and here's Z sub B. With the delta connection. We have two ways of interconnecting the sources, two ways of interconnecting the loads, and we can mix and match those. Which means that we have 4 different possible arrangements when we start matching these up or interconnecting these according to the different options. We have 4 different arrangements. We have our source, and we have our loads. Meaning for the source, we might have Y's, and then deltas, and in the load, we might have then a Y or a delta, a Y or a delta. So that we have a YY, a Y delta, a delta Y, or a delta delta. Interconnection, and you now may be asked to analyze any of those 4 possibilities. Which, if you wanted to see those, here is the YY. Wow. And was that a Y? Is that what you were asking? So here is now, you don't need to draw this, but I would recommend actually when you go home tonight or tomorrow or sometime, you might actually start drawing those and getting a feel for what these actually look like. It probably would help you to actually sketch them to make it sink in. But here is a YY, and what do we have? The source, we have the generator voltage as a phasor. Then we have its impedance, Z sub GA. Then we have a transmission line impedance, Z sub little l A. And then we have the load impedance, Z sub A, or Z sub AN. And you can see then that we have a neutral connector. When we're at the loads, the convention is let's capitalize the subscripts for the terminals, and at the source we're going to use lowercase. In the upper A piece, the current is now going from little a to capital A. That current is actually a transmission line current, but we just abbreviate that just to make it confusing. We call that the line current. In this particular case, that current actually passes directly through that load. So that current is also in this Y-connected load, that line current is also the A-phase load current. The voltage dropped across this A-phase impedance, which I'm labeling V sub capital A capital N, is the phase voltage for the A phase. That's the voltage across the A phase of the load. And if you wanted to find the power in the A phase, the complex power, do you see what you could do? If you knew what V sub AN was, and you knew I sub A, little a, big A, you could just compute V I star with those two, with that voltage and that current. And that would tell you what the complex power of that particular A phase is in this interconnected system. That's the YY. And now you know what's going to happen. Here's the Y delta. The source looks the same. But now what happens down here at the load? Do you see that you now have two different currents that are at play? And in fact, we have a little different voltage to worry about. The line current is still I sub AA. That's still the transmission line current, but when it gets down to the load, what happens? Now it gets divided, doesn't it? Because our load is now in a delta configuration. So now we have to figure out how to relate this line current to this. This is now the A phase load current. That's different than the A phase line current in this configuration. Do you see how the terminology or the wording you have to pay attention to, or it can get you all mixed up? What about the A phase load voltage? What is it in this Y delta configuration? What's the A phase load voltage? Pardon? It says right there. That's why this is really tough, isn't it? I'm just making sure you're awake. It's V sub AB. But that's not what it was in the previous. This is now a line voltage, isn't it? It's from one transmission line terminal to another. So now your line voltage is the same as your A phase voltage in this interconnected system. Whereas before, if I wanted to talk about the line-to-line voltage or the line voltage at the load terminals, that's now different than the phase voltage. Now I have to do this KVL that involves V sub AN and V sub BN in order to figure out what, well, that's kind of an ugly thing, but that plus minus is actually a plus with a phasor bar on top of it. That's V sub AB. That's the line voltage at the A phase, but that's not the same as the phase voltage in the A phase. Do you see how? Yeah, somebody had enough. But by the exam, you have to make sure and keep these clear. What's another? So here, do you see that the A phase line current, the current in the transmission line in the A phase, which is I sub AA, that is definitely not the same as the A phase load current, which is I sub A, capital B. Whereas in the YY, it was the same. The line current was the same as the A phase load current. I want that point to be clear by the end of today's class. Here's the delta Y, and here's the delta delta. And as I said, you can go home and draw these to make them a little bit more ingrained into your thought process. Now what do we want to do? Let's go to a different page. Let's now look at computing complex powers associated with this YY interconnected system. And now this one differs a little bit in that I now have placed a neutral conductor between the two neutrals, which I have two neutrals, one at the source and one at the load. One is called little n, and I'm going to use that as my reference node, and capital N is the neutral terminal at the load. And from this diagram, what I want to do is compute the A phase power, complex power. So let's now say we want the A phase, and that's actually not yet precise enough. If I said the A-phase complex power, you're going to say, of what? If I just said the A-phase complex power, it needs to be of the source, or of the load, or the transmission line. Here, let's make it of the load. So now I'm going to label that S sub A. In terms of what I have on this diagram, how would I compute the complex power of the A phase at the load? The A phase complex power at the load.
You could start by using the current from AA and voltage from A to B line.
So now, which voltage do I use? I like the I sub AA. That's in the A phase. That's going to pass through that Z sub AN, the A phase load impedance. But now, if I want the complex power of the A phase, what voltage do I use? Do I use V sub AB or do I use V sub AN? I want the complex power of the A phase. If I just gave you an impedance and said, here, find the complex power of that impedance, what would you do? You would say, well, I need the current through that impedance and I need the voltage dropped across that impedance, right? And then it would be V I star with the appropriate voltage and the current. If that's the case, what do I need here? VAN, don't I? So now the complex power, does everybody see that? It's not V sub AB. V sub AB is the transmission line voltage of the A phase, or it's just called the line voltage of the A phase, but that's not the A phase load voltage. So you really have to listen. That's why I talk so slow, is you have to listen to what is being said or asked. Is it clear what we're trying to compute? We want the complex power of the A phase. That, you know the complex power expression, that's VI star. For this particular case, it's V sub AN. That's the voltage across the A phase impedance times the conjugate of I sub A, little a, capital A. So this is in fact what we would call the phase voltage for this interconnected load. This is a YY connection. This is the phase current. And in fact, that's the current through Z sub A. This is the voltage across Z sub A. And this is also the line current, the transmission line current in the Y-connected load. Question?
What would be the line voltage for that top?
So now what is the line voltage in this circuit? That's the, so now put in more adjectives. It is just called the line voltage, but really say what's the voltage from one transmission line to another. So the line voltage here would be from terminal capital A to terminal capital B. That would be the line voltage, which is not the same as the phase voltage for this interconnected circuit. Yes.
What would VAA be then?
What would, I'm sorry?
Capital A to V lowercase a.
What would V capital A capital lowercase a?
And capital A lowercase a.
So now what would capital, so that would be, I would call, I think what you're asking is what is this voltage? Let's say now, and actually it depends on which way you do it. I would probably say that we would label that something more like that, and this would be the positive and this would be the negative. And I would call that the voltage dropped across the transmission line impedance. So it's not the line voltage, which you could argue, yes it is, but it's the voltage dropped across the impedance in the transmission line. So the convention is when somebody says what's the line voltage, they're meaning between terminals from one transmission line to the other. Does that help? And I could ask you to compute the voltage dropped across the transmission line impedance. And that would be this capital V sub little a capital A. So you have to just worry about terminology or make sure it's clear. And what I think we've clarified in this discussion is the following. Hopefully it's clear that V sub AB is not equal to V sub AN, where this is in fact the line to line voltage, which most of the time is simply referred to as the line voltage. And this, V sub AN, is our phase voltage, not in general, but in a Y-connected load. Because in a delta connected load, the line voltage is the same as the phase voltage. So it can be confusing the first few times. So if this is now our complex power of the A phase, then what's the total load power? Now we have three loads in our load making up the total load. We have the A phase, the B phase, and the C phase. And we have to account for all three. If somebody says, what's the total load power? And usually they'll be implying the complex power, total complex power of the load. So the total load power you could compute as S sub A plus S sub B plus S sub C. What? Did I call that S sub A? Yes, I did. And if it's balanced, if our load is balanced, if our system is balanced, then in fact S sub A is equal to S sub B is equal to S sub C, and a lot of times we will just call that our complex phase power, S sub phi. So now to make it all mixed up, let's look at what happens, not intentionally, but hopefully to clarify things. Let's say we have a Y delta configuration and somebody wants the formula for the complex power in the load. Here we have, let's say, and I could now be more clear maybe and say this is Z sub AB. Here's Z sub BC. And here is Z sub CA. This is terminal A, terminal B, and terminal C, which we might pull out and say, well, there's A, here's B, and there's C. This current would be the line current, and that's I sub AA. But now how do I compute the A phase load power? What's the formula that I need to compute the A phase load power for this delta connected load? Now you need to say, well, you need to label it more than what you've labeled, because right now the line current really doesn't tell me what I need to compute the complex power. I need the voltage across one of these impedances, and I need the current through that same impedance, and then I can just do VI star. What's the voltage across the A phase load impedance in this configuration? Do you see that it's just the voltage between the A terminal and the B terminal? That's now V sub AB with those subscripts capitalized. And the current is in fact this current, which is I sub AB going through the impedance in the A phase of that load. So that now if I wanted to compute the A phase complex power of the load, this is now for a delta load connection or configuration. Now I take and say, oh, S sub A, the complex power in the A phase, is the phase voltage in that load, which in this case is V sub AB. That's the voltage across the A phase, times I sub AB star, where this is the phase current is that equal to the line current? What's the line current in this diagram? It's little a, capital A. That's the line current, and that's not the same as I sub capital A, capital B. The phase current here in this delta load configuration is not equal to the line current, which is I sub A, A. And what is this? Well, to be in this formula, it has to be the phase voltage of the load. And that's, in this configuration, is in fact the line voltage. And here, I hope that you can see that the A phase load current is not the same as the line current. Depending on how your load is interconnected will impact which voltage you use and which current you use. So you just can't say, tell me the line voltage, tell me the line current. You have to understand what interconnection you have and how to use that information. What's the total load power? Well, again, it would just be the sum of all three phases. And if it's balanced, then you can get away with just computing one phase. And we might just call that the complex power of S phi. Pardon?
You just wrote SB instead of SC.
Two B's or not two B's? C. Just making sure you're awake. Is that okay? Is that better? That's a capital C.
Okay, it just kind of
Looks like an E. Now you're really getting particular.
There we go.
There. So we didn't have an E phase to begin with, so you have to sort of do your filtering. And we'll get into filtering later. Now, what you probably can appreciate is that it might be helpful to learn how to convert between these different interconnections, to convert delta to Y and Y to delta. And if you're looking for impedances to do that conversion, then in the 10th edition of the book, that's back in chapter 9, in section 6. And if you just want it maybe for resistors, that's clear back in chapter 3. But in chapter 9, the delta to Y conversion for impedances you will find in equations 51 through 53. And Y to delta are the next three, 54 to 56. And we will subsequently learn how to convert the sources. That's not yet, let's say, done. But we will assume that you can do the loads, the impedances, but if they are balanced, there's really just a factor of 3 between the two, between the Y's and the deltas. It gets more involved. You have to keep track of which one's where if in fact they're not balanced in order to do the conversions from delta to Y or Y to delta. And that's what those formulas provide. If you just assume that they're all equal, then those formulas collapse into just a factor of 3 between the Y's and the deltas. So now let's look at analyzing three-phase circuits. And in this analysis, we'll establish or use the following notation. We'll have a double subscript notation. And in particular, if we said something like V sub AB, then that's going to be the voltage drop from the first subscript to the second subscript. And what we want to do now is figure out, is it possible, or how can we now extract a less complicated circuit from that three-phase mess? So how do we now look at going from three-phase to a single-phase equivalent circuit? And we will do that for the YY circuit, with the understanding that if somebody gives us a Y delta, well, now maybe we convert the delta load to a Y, and now we have a YY circuit. If somebody gives us a delta Y, then we convert the source to Y, and now we have a YY. If we have a delta delta, then if we don't have any transmission line impedances, then it's somewhat clean to analyze in just the delta delta configuration. But first, to get us started, let's find the current in that neutral conductor. And you did so well before, let me give you another quiz. Can you write a KCL equation, Kirchhoff's current law, at node little n? So let's go back and find the circuit that I want you to now try to analyze. Now you can see it on one screen, maybe. Write KCL at little n. That's your quiz. What is a KCL equation at little n? And I would probably do it in phases or in steps or in stages. What's the cleanest way that you could now write a KCL equation at little n? In terms of some of the variables that are already identified in the circuit. Are all the currents identified that you need? KCL simply says the sum of the currents in equal the sum of the currents out, or the algebraic sum of the currents is equal to 0. What currents are going into little n? I sub 0. And which ones are going out? All of your line currents. I sub AA, I sub BB, and I sub CC. That's KCL. If you wanted more, you would need to continue. So now how would we find an equation for I sub little a capital A? Before I scroll this away, can you now start to try to compute an expression for the current in transmission line A, I sub AA? Maybe you need to identify, since little n is our reference, maybe you could say, well, if you would give me this voltage, that's the voltage at capital N. That's V sub capital N. Now you could say, oh, I know the voltage dropped across those impedances in the A phase. It's just the sum of the generator impedance plus the transmission line impedance plus the load impedance. And the voltage dropped across that relative to little n is V sub A prime N minus V sub capital N. Do you see that? And if you don't, you need to go home and convince yourself that this argument is actually valid. So let me try to write some of that down. And I'm going to get a little bit bigger now. Huh. Good luck with that. And what did we just say? Wow. So now our KCL equation at node little n, we said in terms of general labels or variables, that was I naught, the current that we had labeled in the neutral conductor, was equal to I sub little a big A, I sub little b big B, and I sub little c big C. And now we just write those currents in terms of the voltages on that diagram. I sub 0 is just V sub n over the impedance through that neutral conductor. That's I sub 0. I sub little a capital A was the voltage dropped across all three of those impedances, which was Z sub GA plus Z sub LA plus Z sub, let me just call it A. Likewise, we have I sub little b big B. And finally, I sub little c big C and this, if everything is equal, we'll just call that Z sub phi. And what we want to now think about is the scenario where we are working with a balanced system. And what do we mean by a balanced three-phase system? A three-phase circuit is balanced as long as a few properties are satisfied. If 1, V sub A prime N, V sub B prime N, and V sub C prime N, as long as those three voltages form a set of balanced three-phase voltages. What allows those three voltages to form a balanced set? What do you mean by they're all equal? So their magnitudes have to be the same, but their angles have to be separated by 120 degrees. and in the appropriate relationship depending on whether it's a positive phase sequence or a negative phase sequence. If you chose V sub A prime n as your reference phasor, if that's the one where you drew your t equals 0 line, then V sub B prime of n would be minus 120 degrees behind it if this was the A phase, if this was a positive phase sequence. That's one condition for the circuit to be balanced. The other concerns these impedances. Your generator impedances need to be the same. Your transmission line, or the impedance along the transmission line, needs to be the same in all three phases. And you can see then that I abbreviate that without including the transmission line. I just say line impedance. And finally, the fourth property or constraint for this to be a balanced circuit is for our load impedances to all be the same. We need Z sub capital A to be the same as Z sub capital B to be the same as Z sub capital C. Let me state a fact. If the system is balanced, we can conclude that the voltage at the neutral terminal in our Y-connected load is actually 0. So that's the same as our reference, essentially, which was back the neutral terminal in our source. And you've probably taken enough math classes that if somebody states a fact, you need to have a proof, right? So let's do kind of an engineering proof of that. Let's go ahead and let Z sub phi be Z sub A plus Z sub LA plus Z sub GA. And in our previous formula, we had V sub n's. Let's move all of those to the left-hand side. We have V sub n over Z sub 0, but then we have V sub n over Z sub phi 3 times with negative sign, so when we move it over, that just comes over as a plus. And we have our, if it's balanced, Z sub phi, the denominator's the same, and we have in the numerator V sub A prime n plus V sub B prime n plus V sub C prime n. That's the formula that we want to now write down. V sub n is going to be 1 over Z sub 0 plus 3 over Z sub phi. And that's equal to Z sub phi, V sub A prime n plus V sub B prime n plus V sub C prime n. And you know what that equals. Remember the quiz that you were so quick to answer? Drawing these phasors, if that's a balanced set of three-phase voltages, head to tail, you can add those up and you get back what? 0. This now is 0 over Z sub phi. And we know that this is not equal to 0. We can divide it out, and then we have V sub capital N equal to 0. And that's what we were trying to show or prove. So there's the end of our proof. Drawing a square. So now, what does that say? That says that there is no voltage between the source neutral which was little n, and the load neutral, which was big N. So if there's no voltage dropped across that neutral conductor, how much current is flowing? Boy, I'm going to just go tell Dr. Marcelin, you guys are just on the ball, right? If there's no voltage drop across something, there's no current flowing, is there? There's nothing to push that current. So this deserves a couple of stars, and those could be gold if you want in your notes. Put it on the refrigerator. Mom, look, 2 gold stars. So there's now no current flowing in the neutral conductor. And that actually gives us a couple of options. One option, if there's nothing happening in that neutral conductor, we could just remove it. Nothing happening, there's no current flowing, there's no voltage dropped across it. We could simply remove the neutral conductor. Since we don't need to keep track of that current, it's 0. Or we could replace that neutral conductor with a perfect short circuit since the voltage is 0. So we could replace the neutral conductor with a perfect short. What are our currents if we have a balanced set or a balanced system? What's little or I sub little a big A? That we said was V A prime N minus V sub capital N over Z sub phi. Well, that's just V sub A prime N over Z sub phi. Do you see that each of the other phases will be defined similarly in terms of their source voltage generator? This is now V sub B prime N, and I sub little c big C is V sub C prime N over Z sub phi. What can you tell me about the currents if they have this connection? Pardon? Do they cancel out? Or what do we know about A prime, B prime, C prime voltage phasors? They're not quite all the same. They are a balanced set of three-phase voltages. They differ by this 120 degrees. But Z sub phi is the same, isn't it? So what does that say about I sub A, B, and C? They form a three-phase balanced set of currents. So if you know the I or the A phase, you could give me the B phase or the C phase if I tell you the phase sequence. The upshot of this is we want to be able to solve for the A phase, and then you have the B and the C, because we know they form a balanced set of currents. And that's what I'm going to write after you guys disappear. I'm going to say that these currents now form a balanced set of currents, and that now allows us to extract or look at a single phase, and if we can solve for voltages and currents in that single phase, we could then go ahead and provide information about the other two phases, because we know they're 120 degrees from the one that we just found. We'll pick up at that point the next time we're together.